This video is on the trends of the periodic table. The three trends that we are going to learn about are atomic radius, electronegativity, and ionization energy. Atomic radius is just the size of the atom. Radius is just the definition of the distance between the nucleus and the outermost edge of our atom. Electronegativity is the tendency of an atom to attract an electron, or how badly the atom wants one more electron. Ionization energy is the amount of energy required to remove a valence electron from the atom. So we know if we make an ion, that is either adding or taking away an electron, and that's the energy required to remove that electron. So a high ionization energy, it's going to be difficult to remove an electron. A low ionization energy, it's going to be easy to remove that outermost electron. So to do this, we're going to, or to look at these trends, we're going to draw Bohr models of a couple of specific elements. I'm going to draw the Bohr models for hydrogen, helium, fluorine, lithium, and francium. So take a moment here, pause the video, and draw those 5 Bohr models. All right, so I went ahead and drew my Bohr models. So we have hydrogen, and we notice that hydrogen up here, it just has one energy level, one valence electron. Helium is one of our noble gases. Its outermost orbital is full. It has its 2 electrons, so it's happy. In group 2, we have lithium, which has our 2 energy levels, and its outermost energy level has 1 valence electron. Fluorine has 7 valence electrons. It wants to have 8 to have the outermost shell filled. And then down in the bottom left, we have francium. It has 7 rings. 1 through 6 are completely filled, and then on that 7th ring, after 90 or 80 some electrons there, it has 1 lonely valence electron on the outside. So we're going to comment on size, electronegativity, and ionization energy. So size is how big it is, its atomic radius. So as we go across our table, as we go from lithium to the next, to the next, to the next, to the next, we get to fluorine, and then our noble gases, every time our atom gains an electron and a proton. And when it does that, it starts to want that electron more and more because it wants to gain one more electron and one more electron because it wants to have that nice filled outer shell. It's called the octet rule. It wants it filled, and it wants to keep those electrons close. So as we go across, my atom starts to hold those electrons closer and closer to the nucleus, and it actually gets smaller as we go across. So as we go across our periodic table, our size decreases. Okay. We'll notice though, as we go down a column, as we go down, we add an energy level, an energy level, an energy level, and so on and so on. When we look from lithium to francium, clearly our size gets bigger as we're adding energy levels. So as we move down a column, the size increases. Okay. So we're going to get asked questions like, which is bigger? Which has a higher atomic radius? Which has a lower atomic radius? So we're looking at lithium or rubidium. We know that rubidium is here, lithium's here. As we go down our column, we get bigger. So that means that rubidium is bigger than lithium. Then we have sodium and chlorine. Well, sodium is a metal, chlorine's a nonmetal. Sodium's on the left, chlorine's on the right. So as we go across our periodic table from sodium across to chlorine, we're adding electrons, and those electrons get held tighter and tighter and closer to the nucleus. So as we go across, we notice that we get smaller, our size decreases. So that means that sodium is going to be our larger atom. Next, we get to electronegativity. Electronegativity is the tendency of an atom to attract an electron, so how badly it wants an electron. Like I said, as we go across, we start to hold our electrons closer and closer and closer. That means that our atom wants to gain more and more electrons. So as we go across our periodic table and add more and more electrons and hold them closer and closer, we're going to want to hold them really, really close, and we want those electrons more and more. So as we go across our periodic table, our electronegativity increases. Okay. And as we go down our column, well, we want those electrons, sure, but we're filling energy levels. And this nucleus, as far as its pull go on these outermost electrons, it can hardly touch them. So its want for one more electron, it's kind of like, meh, I don't care. I have a lot of electrons, I'm okay. So it doesn't really want an electron anymore. So as we go down our columns, our electronegativity decreases. So which is more electronegative, lithium or rubidium? Well, rubidium is further down. It has a lot of shielding of those inner electrons on the pull of our nucleus. And our atom just is frankly too big to want one more electron. So lithium is more electronegative than rubidium. Now from sodium to chlorine, chlorine's much smaller than sodium. It's holding those electrons really tight. It wants one more electron to gain that full octet. So chlorine is the most electronegative of the two. Now something to note, fluorine is the most electronegative. So when we're looking at our periodic table, the closer we get to fluorine, this guy up here, the closer we get to him, the more electronegative we get. Thus, the closer we get to francium, the less electronegative. So if we think of our periodic table in these two corners, more electronegative is fluorine, less electronegative is francium. And then lastly, we have our ionization energy, or the energy required to remove an electron. If I'm going across my periods, my electrons are getting held tighter. I want one more electron. So if I try to remove one of those electrons that my atom wants, it's going to put up a fit. So it's really, really hard to remove an electron from something like fluorine, or even more so from my noble gases. My noble gases are happy. Their octet is full. Therefore, they don't want any more electrons. They have zero electronegativity. But if you were to remove one, it would have the highest ionization energy. It is the most happy with the electrons it has. So as we move across a period, the ionization energy increases. Okay. As we go down a column, my ionization energy is going to decrease. You might ask, well, why does it do that? Well, it decreases as we go down. We look at lithium. Lithium has its electron close to its nucleus. That nucleus can pull on this electron. If we get down to francium, here's my nucleus. I want to pull on this electron. I'm also already pulling on all of these electrons first. So these electrons here are shielding that pull from the nucleus, from preventing that nucleus from actually pulling on that electron. So if I were to go up to francium and say, I'm going to borrow this electron out here, he'd say, oh, sure, you can take it. I don't want it. I can't even tell that this electron is out here. So it just easily gives up that electron. It takes almost no energy to pull that off whatsoever. So you'll notice our trend for ionization energy is the same for electronegativity except for our noble gases. Noble gases and ionization energy have the highest ionization energy. Electronegativity, they don't want that extra electron, so they don't care. So they have no electronegativity. But so if I were to decide between lithium or rubidium, which has a higher ionization energy, well, rubidium has tons of shielding of those electrons. Therefore, rubidium has almost no ionization energy compared to lithium. Lithium would know if it lost that outermost electron. So lithium has the highest. Sodium to chlorine, chlorine's one electron away from having that full octet. So if I were to remove one of those electrons, it'd be really upset, and it would take a ton of energy to pull that one of those 7 valence electrons away from it. So it would have the highest ionization energy out of the two of them. So we're going to practice more of this the next day. But just know that a big things we're looking at is it all comes down to the size and its valence electrons. Does it have that full outer shell, or is that outer shell just have one electron and there's tons of electrons shielding the pull of the nucleus to that one? And then if we just remember where francium is and where fluorine is, and think about our full outer shells, the trends become really easy.